Okay, so first of all, for the people who didn't do the lab exam and the quiz on Wednesday because of the weather, um, so what we'll do, all we're doing in lab this week is the post test for that intuition test, and it takes at most half an hour. So, and the lab exam is short too, so you'll have no trouble finishing all of that stuff in one lab period. I think most people will probably finish all that stuff in like an hour 15 or something. So during your lab this week, if you missed the lab exam, we'll do the intuition test and then the lab exam after and the quiz after if you need to do that too. Is there anybody who is planning to do lab tonight who missed the lab exam? Oh, yeah. Okay. Two. Okay. Great. Um, and then second, I just gave back exam 4. Anybody have any questions about that? Any problems you'd like me to go through? Yeah. Yes. Okay, so that's the one where there's an incline and a box sliding on the incline. And we know that the angle of the incline that it makes with the horizontal is 30 degrees. And we know that at this instant, the block is sliding up the ramp. So that's the direction of motion. It has a mass of 5 kilograms. And we want to figure out the acceleration vector and use that to figure out whether it's speeding up or slowing down. Okay, so first, the coordinate system that we're going to use has the y-axis pointing straight out of the surface. So the x-axis has to be that way. A free body diagram of the block has the weight force straight down. That's 5 times 9.81, so 49.05. And then the normal force coming out of the surface. So this is N. And then the only other force is the friction force. That has to be the opposite direction as the motion. So that's going to be this way. And the coefficient of friction is 0.2. And we're going to multiply that coefficient 0.2 times this normal force. So this is 0.2 times that N value. So I'm going to draw a picture so we can figure out what the components are of that weight force. This angle here is 30 degrees. And so that vector, if you go counterclockwise from the positive x-axis, it's 90, 180, and then 30 degrees short of making it to 270, so it's 240 degrees. So this theta is 240. And so that weight force is 49.05 times cosine and sine of 240 degrees. And that comes out to be negative 24.525, negative 42.479. So then Newton's second law, we have this vector we just calculated, negative 24.525 negative 42.479 plus 0n. And then that friction force is in the negative x direction, so plus negative 0.2n, 0. And remember, this end here is not, this isn't saying negative 0.2 newtons. I see that pretty often. This is saying that whatever you get for this value n, you plug it in there and multiply it by 0.2. And all that's equal to the mass of the body, 5 kilograms, times the acceleration, a0. And then use the y equation to calculate n. So that gives you that n, negative 42.479 plus n is equal to 0. And so n is equal to positive 42.479. And that's newtons. So I'm always going to show the normal force with the like scripty things on the n, and newtons is just a plain uppercase N, so you can tell those apart. And now we'll plug this value for n into the x equation. You get negative 24.525 minus 0.2 times 42.479 is equal to 5a. And you get that a, the value of that variable a, is negative 6.61, something like that, meters per second squared. And now take this variable value and plug it into this thing here. Is the acceleration vector. So the acceleration vector is negative 6.610 meters per second squared. Or you could also think of this as an acceleration of 6.61 meters per second squared in the negative x direction, which is this way down the ramp. And so now, to figure out whether it's speeding up or slowing down, look at the directions of the velocity and the acceleration. If they're the same, it's speeding up. If they're opposite, it's slowing down. In this case, we have the velocity going this way and the acceleration going this way, so it's slowing down. Any questions about that? Any other questions on the test you want me to do? Yes. Okay, yeah. Our final is on the 17th at 6. And then if you would rather have a couple more days to study, if you can figure out a way to make it work and come to the day class on Thursday the 20th, you can do that too. So that's at 2 o'clock. And I think it's in the, yeah, it must be in the regular classroom, so just right next door, 1328, if you want to do it during the day. Okay, no more questions about the test? Okay, so now we're going on to a new topic, and that's conservation laws. And this is split up into two different areas. The first one is conservation of linear momentum. Um, this is useful for collision problems. That's mainly the only time you would ever use conservation of momentum. And I'm going to say a little bit about this, but we're mostly going to skip over this and move on to the stuff that's going to be more useful if you go into physics 2. Um, so we'll touch on this briefly. And then the second thing we're going to talk about is conservation of mechanical energy. Um, so we're going to spend more time on conservation of mechanical energy. This is really useful. And this idea is going to come up a lot in physics 2 and whatever. Conservation of mechanical energy. So this is going to be useful when the only forces that do work are called conservative forces. Talk about what all those things mean, and then we'll go into some calculations. The sort of interesting thing about conservation of mechanical energy, this approach, is that you can actually solve all the same kind of problems using a force analysis like we've been doing that you can with conservation of mechanical energy. It's just that there are some problems where this is easier, and there's some problems where a Newton's law approach is easier. So you kind of, like, one of the real tricks to getting into conservation of mechanical energy is being able to identify when it's a good idea to go in this direction and when it's a good idea to go in that direction. There isn't really a wrong answer, but practically speaking, there's a big difference between the two approaches. Okay, so first, what does conservation mean? Conservation means properties stay the same. So if you're like a conservationist, um, if you're really a conservationist, you shouldn't go around planting trees. You should stand around with a waiting to plant a tree until one falls down, and then you can quick replace it. You know what I mean? So it's not just about like it's not about like um, moving the world in a certain direction or whatever. It's saying things stay the same. So if we talk about conservation of linear momentum, we're saying that at instant 1 and at instant 2, the two instants you're looking at, if you calculate the total linear momentum, it's the same at those two instants. That's what we're talking about. Okay, I'm going to start with conservation of linear momentum. And first we have to define what linear momentum is. So linear momentum and I'm going to denote it as a lowercase p that I'm sure is connected to the Latin word for this or something. vector. So the linear momentum p is equal to the mass of the object that you're looking at times its velocity vector. So m is the mass of the chosen object, and v is the velocity of the chosen object. There's two things to notice about this. The first one is that the units of momentum are units of mass times units of speed. Well, actually, let me write it. Units of mass times units of length divided by units of time. And so if you're in SI units, that's kilogram meters per second. And the second thing to notice is that linear momentum is a vector. So it has a magnitude and a direction. See, when we start talking about energy, that no type of energy has a direction. Energy is just a scalar value. It's not a vector. Linear momentum is different. You have linear momentum in this direction or this direction, and those are different things. Okay, so for example, imagine a train car that we're looking at from above. Okay, so let's say it's going this direction with a speed of 10 meters per second. And let's say that it has a mass of 10,000 kilograms. And let's say that we're using a coordinate system like this. What's the linear momentum of this train car? Okay, well, the mass is 10,000 kilograms. The velocity is 10 meters per second in the positive x direction. So 10, 0 with units of meters per second. And so the linear momentum is mass times velocity, which is 10,000 times the vector 10, 0. And that gives 100,000, 0 for a vector with units of kilogram meters per second. Okay. And intuitively, you can sort of think of momentum as how difficult something would be to stop. You know, like the magnitude of the momentum tells you something about that. Um, like, for example, this train car, you would not want to try to stop with your hands because that value of 100,000 kilogram meters per second is very large, you know? Whereas, like, a baseball that's going 10 meters per second, a baseball only has a mass of zero point 0.1 kilograms. So you'd have a momentum in the same direction, but with a value of 1 kilogram meter per second. Like, okay, that's a lot safer. Okay, so conservation of linear momentum now says this. Along any coordinate system axis where the net force on the chosen object is 0, um, the linear momentum of the chosen object is constant. And just like before, you know, like there are a lot of times where when we're using Newton's laws, we'll isolate like two different objects, treat it as a single thing. You can do that here too. Um, so you can have a chosen object or a system of objects. Um, so let me show you what this can do in terms of collisions. Um, so let's say that we start with a train car of 10,000 kilograms with a velocity of 10 meters per second. And let's say that it hits another train car with a mass of 15,000 kilograms that's at rest. Um, what do we know about the velocities of the cars, of the train cars, after the collision? Okay, you follow what I'm trying to draw. So one train's coming in at 10 meters per second, and it's going to collide with this second train that's at rest. And, um, you know, like after the collision, you know, both of their velocities are going to be affected by this collision. What's going to be the velocity that comes out of this? And so what we know is, so we're going to make our system, both of the train cars together. So during the time of this collision, what's going to be the net force on these objects? Well, since we're isolating both of them as a single system, remember the net force, we only care about external forces. And so if we're isolating both of those as a single thing, when they collide, the contact force between the two is internal to the system. And so that doesn't exist to us, okay? So that contact force of the collision is an internal force. And so it doesn't contribute to the net force. By the way, you want to know why this is? So why is it that, like, if you think when we're doing Newton's laws, okay, we sort of treat internal and external forces the same way we do here. Why is it that we always represent, if we're doing a free body diagram, we show the weight force, and then we go around the boundary finding all the external forces, but we don't care at all about the internal forces. And there's tons of internal forces on anything, you know, like even this table, there's molecules bouncing around. And if we had to deal with all those, that would be a major pain. We're sort of lucky we don't have to, you know. But why is it that we can just leave all those internal forces out and worry only about the forces applied by the surroundings to the boundary? The answer is that any forces, well, the answer comes from Newton's third law. Any forces that are part of the system applying a force to another part of the system come in pairs because of Newton's third law. So like if you think of, like, there's a force that the right side of the table is applying to the left side of the table. Okay, that's a force, but the left side is also applying an equal and opposite force to the right side, and those are both forces being applied to our system, and so they cancel each other out. The only places where those forces don't cancel each other out is on the boundary, because then you have the surroundings applying a force to the table. Well, the table's also applying a force to the surroundings, but that one doesn't count in our system because we only care about the forces on our system. So the boundary is the only place where the forces don't cancel out in pairs because of Newton's third law. And so it's the same thing here. When these two are in contact, these two crash into each other, there's some big force that the 10,000 applies to the 15,000. The 15,000, though, applies an equal and opposite force to the 10,000. They cancel each other out, and so they don't contribute to the net force. Okay, so before the collision, momentum of the 10,000 kilogram car is the mass of 10,000 times the velocity vector of 10, 0. We get a momentum of 100,000, the x direction, 0 for y. The units are kilogram meters per second. The momentum before the collision of the 15,000 kilogram train car is 15,000. That's the mass. It's at rest, so the velocity vector is 0, 0. And so the momentum of the second one is 0, 0. So the total momentum of our system is 100,000 plus 0. So it's 100,000 in the x direction and 0 in the y direction. So now let's think about after the collision. Since F net is 0 during the collision, we know that the total momentum after the collision also has to be 100,000 for x, 0 for y. Okay, so what does that tell us about the velocities of the individual cars, which is what we really want to know. But the key thing here is, so we do know that after the collision, the total momentum has to be 100,000 for x, 0 for y. But there are infinitely many possibilities. Infinitely many possibilities that satisfy this requirement. So for example, after the collision, we could have 10,000 kilogram cart going, well, at rest. And we could have the 15,000 kilogram cart going. What's 100,000 divided by 15,000? Is that 6.6 repeating? Yes. 6.6 repeating meters per second. So that's one possibility. Another possibility is those two could stay in contact with each other. That's what would happen if the trains linked when they collided. And so you could get a system where they stay together and the whole thing moves at 4 meters per second. Because now we have a total mass of 25,000 kilograms. Total momentum is 100,000, so divide 100,000 by 25 and you get 4. So that works the same way. That would be fine too. And there are infinitely many answers, but not everything works. So for example, let's say after the collision, the 10,000 Newton or the 10,000 kilogram train car is going this way at 2 meters per second. And the 15,000 kilogram cart is going this way at 10 meters per second. That looks like a reasonable possibility, but if you add these up, you get a momentum for this one of negative 20,000, 0. The momentum for this one is 15,000 times 10, so positive 150,000, 0. And so P total would be 130,000. Okay, so the key thing here is notice conservation of linear momentum limits the possible velocities of the objects after the collision. You know, it puts limits on the possible velocities after a collision. But it isn't ever enough to solve by itself. And then if you think physically about what happens when two objects have a collision, it sort of makes sense that this isn't enough. So let's say you have two 1 kilogram circular objects, and you say they're moving 2 meters per second towards each other and they collide. And someone asks you, what are they going to do after they collide? And you think about it and you're like, oh, well, I need to know more about what these objects are made out of. You know, like if they're made out of, if they're super balls, they're going to bounce apart in a certain way. You know, if they're rocks, they're going to bounce apart in a different way. If they're, Play-Doh or something, they're just going to smush and stick together and fall down, you know. So it makes sense that conservation of linear momentum isn't enough to determine everything about how a collision works. If you want to determine everything, you need more information, which basically comes down to a mathematical description of what the two objects are made out of, you know. Um, so you need additional information about the nature of the collision. Okay, I think that's all I'm going to say about that. And let me do one problem. Okay, so let's say um, let's say a person jumps up into the air oh, my picture is getting too tall, and catches a football. Okay, so the football is coming in this way. Let's say the mass of the person is 100 kilograms, and the mass of the football, let's say it's 1 kilogram, just to make it uh, easy numbers. Um, and let's say that the football, right before the football hits the person's hands, let's say it's going, I guess, 15 meters per second. Um, and so if the person catches the ball, what is the combined velocity of the person and the ball after he catches it? Okay, so that's after the collision's over. He's holding the football in his hand. It knocks him back a little if you think about it intuitively. And both of those two together have a combined velocity. It has to be the same because he's holding on to it. Um, so what's the combined velocity of the person and the ball? Okay, well, first of all, um, in this in this view, so if I use a coordinate system like this, uh, is the net force, the net external force in this system zero? I said in that tone where you're like, no. But there's weight acting down on both of these, right? So net force is zero. It's not zero. Uh, Weight's acting down. Nothing is offsetting that. Net force is not zero. So instead, let's take a view from above. Yeah. Yes. That's important because otherwise there would be a net force from the ground. You know, friction would be keeping the person from moving back. Like if a football comes to you, someone throws a football at you hard and you're standing there, as long as you stay standing up, you don't go anywhere. Right. Yeah. But if you were standing in smooth soled shoes on ice, you know, on warm ice, so it's really slippery, someone throws a football hard at you, you'll actually drift back a little bit. And that's because of conservation of momentum. So that's basically what we're calculating here. So we're going to take bird's eye view, top down view. So here's the football coming in with a velocity of 15 meters per second. And here's the person waiting for it. And now in neither of these two axes is there any external net force acting. So there's no net force on the system in this coordinate system. And so now we can calculate before the catch, before the collision, the total momentum is 1 kilogram times the velocity vector 15, 0 plus 100 kilograms times the velocity vector 0, 0. And so before the catch, you just have a total momentum of 15, 0 kilogram meters per second. And now after the catch, well, now they both have the same velocity. So the easiest way to think of it is let's just treat it now like it's all one system with one velocity. So P total is the combined mass of the system. That's 101 times the velocity vector, which is, we can just calculate both of these two components. And so conservation of linear momentum says 15, 0 is equal to 101 times Vx, Vy. The x equation says Vx is 15 over 101. Can someone calculate that? 0.149. The y equation says Vy is 0. And so after the catch, the combined velocity was 0.1490. It's not very much because the mass of the person is so much bigger than the mass of the ball. You know, if instead the ball would have been hovering in space and the man would have charged at 15 meters per second, it would have, after the collision, been moving at almost 15 meters per second. But you can see the effect of the two things drifting away because of the collision. Yes. Well, I chose my view of the problem so that gravity would not appear in the coordinate system. So if you want to know what's, okay, so this calculates the velocity. So this calculates the velocity going this way. It doesn't tell us the velocity going down. Okay. The velocity going down, we can't really use, well, not really, we can't at all use conservation of linear momentum because there's a net force going down. So we got around that by just saying we don't care about that. Let's choose a view where the coordinate system is like this, and then we can use conservation of linear momentum. Okay. Any other questions about that? And what about the fact that, the thing that I was saying, like conservation of linear momentum by itself is never enough to figure out the velocities of the two things. You have to know something about the nature of the collision. Well, when we said that when we required that the ball and the person travel together after the collision, that was giving it the information, the extra information we needed about what the collision is like. It says, okay, they hit each other and they stick together. Okay. But if you wanted to say that the ball bounces off with a certain, loss of energy or whatever, you could do that. It would just make the math more complicated. But you always need to say something about the nature. This is the easiest case where, like, when you're doing these problems, you're always hoping for problems where they're going to travel together after, because then after the collision occurs, you just say that they're treated as a single object. Okay, that's all I'm going to say about conservation of momentum. So that's all. So now we're going on to conservation of mechanical energy. Um, and conservation of mechanical energy says if okay, the only forces that do work on an object. Okay, that word has a definition. We need to talk about what that is. But if the only forces that do work on a chosen object are conservative forces, we have to define that, then um, the potential energy of the object plus the kinetic energy of the object is a constant. Okay, so PE is what I'm going to call, how I'm going to label potential energy. KE is what I'm going to call kinetic energy. And in order to do this stuff, we have to know what work is. We have to know what the definition of conservative forces is. And we have to know what potential and kinetic energy are. So the setup for this is defining those four things. So I'm going to start by talking about work. And work is the meaning of it in physics is a change in energy that's caused by the application of a force. Okay, so there are a lot of ways to change something's energy. Energy shows itself in a lot of different forms. Like, for example, if you raise the temperature of something, its energy is going up. But normally, the easiest way, in the easiest cases to think about, if you're going to raise the temperature of something, you're going to do it by putting something with a higher temperature next to it and letting energy flow from one thing to the other thing. Okay, that is not work. Even though that's changing the energy of the chosen object, it's not doing it through the application of a force. It's doing it through the application of a temperature difference. So that's something else. So we're only talking about changes in energy that are produced by applying forces to things. Okay, so like right now, I'll explain this a little more as we go, but when I lift this up, I'm increasing its energy. Okay, and I'm doing it by applying a force to it. So I'm doing work on this thing when I lift it up. Or also, if I smash it against the wall, um, I'm increasing its energy by making it go faster by applying a force to it. Um, so the work, um, the work that's applied to an object um, between instant 1 and instant 2 is, the work will be capital W, and that's equal to the force that's applied to the object dot product with the displacement of the object between instant 1 and instant 2. And the meaning of the dot product is you take the x components and multiply them together, and you add that to the y components multiplied together. Where f vector is, so that's the force vector applied to the object. And d is the displacement vector of the object between instant 1 and instant 2. We're not going to do these calculations, but the intuitive result, the thing that you should keep in mind about this, is that if the force vector is within 90 degrees of the object's path, then W is greater than 0. Call that number 1. If the force vector is more than 90 degrees from the object's path, then the work is less than 0. And if the force vector is exactly 90 degrees from the object's path, W is equal to 0. And what these mean, if W is greater than 0, that means that this force is increasing the energy in the object. So the object's energy increases. If work is less than 0, that's taking energy away from the object, so the object's energy decreases. And if work is equal to 0, the object's energy stays constant, it doesn't change. Okay, so that's all you have to know about work. Let's talk about units here. So this is units of work and any other kind of energy. You know, work has to do with, it's a change in energy, so it has the same units as energy. The work and all other forms of energy We know from the definition of work, like if you look at how you calculate it here, you have units of force times units of length. And so you can think of that as units of force times units of length, or you can break up um, force into units of mass times uh, units of length. And now we have those squared divided by time squared. The SI units, that would be a Newton times a meter, which is equivalent to kilogram meters squared per second squared. And because we use this so often, we give it its own name, the joule, capital J. Okay, so the next thing we have to define, that is all we need to know about work. But now let's talk about kinetic energy. We're just going to go through, define all of these four things. So kinetic energy. So let m, lowercase m, be the object's mass. And capital V, let that be the object's speed. Then the kinetic energy of the object is 1/2 times the mass times the speed squared. If you, instead of having the object's speed, normally up until now, it's a lot more common that we're dealing with velocity components than with speed. Um, so if the object, instead of being given the speed, you're given the velocity vector. So let's say the object's velocity vector is vector v. Then you can calculate the kinetic energy as 1/2 times the mass times the x component squared of the velocity plus the y component squared. So just depending on what you have, those are the two ways you can calculate it. So one thing to notice, well, two things to notice. The first one is as something goes faster, it has more kinetic energy. So as the speed increases, the object has more kinetic energy. And then this is sort of a surprising one, and it's sort of important for an intuitive understanding of energy. That is kinetic energy. And this is like every other form of energy, like all forms of energy, is a scalar, not a vector. So energy doesn't have any direction. Uh, you know, when you talk about a force, you apply a force of 50 newtons in that direction or whatever. But there's no such thing as an object having energy in this direction or energy in that direction. It's just something it has, like mass. Okay. Um, so energy is directionless. And really, that gets at one of the reasons that doing energy calculations is nice in a lot of cases. You can get information without worrying about what's happening in all these different directions. A lot of times the math is simpler because you're throwing away all this directional information. And if you're looking for the right kinds of things, you can still calculate, what you're looking for. Um, okay, let's start to talk about conservative versus non-conservative forces. Okay, so a force is conservative if knowing an object's location is enough information to know the force applied to it. Um, we're only going to deal with two types of conservative forces. So for us, that's just first, the weight force, the force applied by gravity. And second, the force applied to objects by springs. That seems like sort of a funny, like uh, oddly specific thing to be worried about. It turns out that spring forces are important in engineering and physics because a lot of things can be uh, represented as springs, but that's what it is. So weight and the force is applied by springs. Everything else is a non-conservative force. Okay, so let me go through sort of an explanation of how this works. Um, so let's say that the object we're looking at is this tape dispenser. Um, so first, let's think about gravity. If I tell you the location of this tape dispenser, and let's say we know its mass, let's say it's 0.2 kilograms or something, is knowing its location enough to know the force vector that gravity applies to it? It is, and in fact, with gravity, we don't even have to know the location. We know that the force acting on it is mg pointing down, right? So if I tell you the location's here, that's enough to know the force. If I tell you it's here, that's enough to know the force, and those two forces are the same. Okay, well then the weight force applied to this meets the requirements of a conservative force. Okay, so you give me the location, I'll give you the force. And now think of a spring that's attached to the wall, and we know how stiff the spring is. And I say, okay, no, this thing's pulled, we take this and stretch out the spring to here. Is that enough information to know the force the spring's going to apply to it? And if I stretched it out here, you know that the spring will be pulling on it, trying to pull it back that way. If you know the stiffness of the spring, that's enough to know how hard it's going to be pulling. And I guess sort of the key idea is, does it matter whether I first moved it to here and then to here and then back to this spot versus doing this 50 times and then back here and then here? The path that it follows doesn't matter. All that matters is how much is that spring stretched or compressed. So if you give me the location of this object, that's enough for me to calculate what the force is. Okay. So those are the two conservative forces. The location is enough information to calculate the force. So now let's see how it works with a couple of non-conservative forces. Okay. The most obvious one, I think, is friction. Like, let's say that this is the location we're going to deal with. Is knowing that it's at this location enough to specify, to figure out what the force is? Well, we know friction depends on the direction that it's sliding. So if it comes to that location sliding this way, the friction force is like that. If it comes to that location sliding this way, the friction force is like that. So clearly the location of the object isn't enough to determine the force. Any questions about that? Then the normal force, at first thought, you might think that's a conservative force, because right now its normal force is just equal and opposite to its weight force, right? But if it's here, right now it has a certain normal force. If I push down on it like that, now it has a higher normal force. It still has the same location. So where it is not enough to specify the force. Okay. But the easy way to remember what's conservative and non-conservative, so that's sort of the philosophy of it or whatever. But the easy way to remember is it a weight force? Is it a spring force? If it's not, it's non-conservative. Well, let's stop there, and I'll finish this next time, and we'll be able to do problems after next class.